This video is about evaluating a function, and we'll first recall, importantly, something called function notation. As you may recall, this is when we see something like f and then in parentheses x. We read that as f of x, and then it's equal to some rule, and that rule defines the function we're given. To evaluate a function, especially using function notation, let's consider this pro tip. When plugging a value into a function to evaluate, follow these basic steps. First, we're going to rewrite the original function, but with blank parentheses in place of the variable. Secondly, we're going to write the input value inside each set of blank parentheses from step 1. And thirdly, we'll just simplify the result. Let's consider the following example. We'll let f of x be defined as a quotient, the numerator being 25 minus x, over the denominator being 5 plus x. We want to evaluate the following. The first example is asking us to find f of 3. Well, as we know, this means 3 is the input. Now, to follow our pro tip, we're going to rewrite the function but use blanks instead of the variable. So I'm going to rewrite that as 25 minus blank for the numerator instead of 25 minus x, and then the denominator will be 5 plus blank instead of 5 plus x. Once the blanks are in place, and if it seems annoying to do this at first, trust me, it saves lots of points. Our next step is to go back and put our input value of 3 in each blank. And then we simplify the result. So our numerator is 25 minus 3, which is 22. And our denominator is 5 plus 3, which is 8. Of course, always reduce if possible. 22 over 8 is really 11 over 4. And that is our function output value. So when 3 is the input, 11/4 is the output. In our second example, we want to find f of negative 5. The same f function is being used, so we'll copy it again, putting blanks instead of the variable x. In each blank, we'll plug the input. This time it's negative 5. Now, be especially careful with negative inputs. The parentheses should do their work and help you avoid mistakes here, but definitely be careful with double negatives and things. So in the numerator, we have 25 minus negative 5. That's really 25 plus 5, or 30. In our denominator, we have 5 plus negative 5, but 5 plus negative 5 is actually 0. That's a problem. We can't divide by 0, which means we'll have to say that this is undefined. For our third example, we want to find f of 1/2. We're using the same f function, so again we'll copy it down with blanks instead of the variable, which means 25 minus blank instead of 25 minus x over 5 plus blank instead of 5 plus x. And in each blank, now we're going to plug the 1/2, our input value. So this, of course, is some annoying fractions, but we can handle this probably with a least common denominator for each of these expressions. If I do that for the numerator, 25 minus 1/2 is really 50 over 2 minus 1 over 2, or just 50 minus 1 over 2. The denominator would be 10 over 2 plus 1 over 2, or just 10 plus 1 over 2. Okay, so altogether simplifying, this would give us 49 over 2 over 11 over 2. If we flip and multiply, we'll end up with 49 over 11 for our simplified results. Our next example is requesting that we find f of x squared minus 1. Now notice in the input place we have x squared minus 1. It's not just a single number, it's an algebraic expression. Well, we treat it no differently than we've been doing with the number inputs we've had so far, which means we're going to copy our function with the blanks in place, but this time I'm just going to leave the blanks to be maybe a little bit wider so that I can fit the larger input in them. So I'll have 25 minus blank in the numerator. In the denominator, we'll have 5 plus blank. And the blanks are just a little bit wider because now we're going to go back and put our input in the blanks, which happens to be x squared minus 1 in both input locations. And now we simplify. So let's go ahead and distribute our negatives to start combining. In the numerator, we'll have 25 minus x squared plus 1 if I distribute the negative to both terms in the parentheses input. In the denominator, we have 5 plus x squared minus 1. We can combine the 5 minus 1 to get 4. So we'll call that 4 plus x squared. And then we'll clean it up a little bit more. In the numerator, we could write this as 26 minus x squared. And the denominator, we'll leave it as 4 plus x squared. Now, if you think back and recall all the rational simplifying we've done already, you'll recall that you cannot cancel these x squareds. They're not factors, they're terms, and so since they're attached to something else with addition or subtraction, they're not eligible to be canceled. We cannot cancel those. We also, for the same reason, cannot reduce the 26 over 4. Those are not factors, they are terms, and so we actually have to leave this expression just as we see it. Now, if either the numerator or denominator of this fraction was factorable, we would factor and then see if we could cancel matching factors, but neither one is. In our next example, we want to find what's called the difference quotient. It's a very famous and useful quotient or fraction that you'll see. It's defined as f of x plus h minus f of x all over h. It has those three key parts. Now you'll notice the numerator is just a couple function notation expressions, f of x plus h and f of x. Now we have to have some kind of function given. In this case, they tell us that f of x is defined as 2 over x. So let's go ahead and find each piece of this difference quotient and then put it all together. It will definitely involve some simplifying by the time we make it to the end. Some color coordination will help usually on this. So we're going to consider the first expression of the numerator, f of x plus h, and I will do that in a color green. Now, this is just going to be using what we already understand for function notation. F of x plus h means I'm plugging in x plus h for my function. So I'll write f of x, but I'll write it as 2 over blank instead of 2 over x. And in that blank, I'll put x plus h. That's the input value we're given. Next, we subtract, and then in the difference quotient, the second term of the numerator is f of x. Well, that's just our original function. So we'll just put minus and then 2 over x. We're not even plugging anything in for x other than itself there. And then this is all over the value h. The only thing left to do is to simplify this expression, but this is certainly not a quick simplification. This is a complex fraction where we'll have to combine terms in the numerator with an LCD. And for the expressions x plus h and x, our LCD would be the product of those x times x plus h, which means overall this expression could be 2 times x minus 2 times x plus h all over x times x plus h as the LCD. Now that's the major numerator, which is all still over h. Let's start to clean things up. If we take it another step, we could distribute the 2 in our numerator and eventually end up here with 2x minus 2x minus 2h over, now we have x times x plus h in the minor denominator, and then that's all over h. So we can simplify that just by multiplying the h times the x plus h. Then we'll continue simplifying by noticing that in the numerator we have 2x minus 2x, those cancel right out. That leaves us with a numerator of negative 2h and a denominator of h times x times x plus h. But then we can cancel these x's since they are factors not attached by addition or subtraction to what is next to them, leaving us with a final result of negative 2 is the only thing left in the numerator, so 2 over x times x plus h. And that is as simplified as we need it, so we'll stop right there. And lastly, we'll also consider how to evaluate for a piecewise function. A piecewise function is a specific type where the function is defined in pieces. So our first example here states f of x equals, and then you'll notice it splits into a curly brace holding two different pieces. The top piece is defined as x plus 2, but only if x is less than or equal to 6. The second piece below it is defined as 5, but that's only if x is greater than 6. Let's consider how this works when we're trying to evaluate various inputs. Our first input is to find f of 2. Now with a piecewise function, we have to take the input, which in this first example is 2, and then run and figure out which piece it will fit in. The conditions on the right side of a piecewise function, which we read earlier as, the first piece is if x is less than or equal to 6, the second is if x is greater than 6, those piecewise definition criteria determine which piece to use for a given input. So with an input of 2, that would clearly fit in the case where x is less than or equal to 6. So that's the only piece we use, the first one, which means f of 2 is going to be, I'm going to use the first piece, I'm going to rewrite the x with a blank so that our first piece is written as blank plus 2 instead of x plus 2, and in the blank we'll put the number 2 as our input, and then we'll evaluate this just as 2 plus 2, which is 4. It helps to understand with a piecewise function that we should only be using one piece at a time. We just have to figure out which one to use based on the input value. The second example asks us to find f of 6. Well, again, we'll evaluate where or which piece that would fit into. And if you go look at the two conditions, the first one is if x is less than or equal to 6. The second one is greater than 6. Well, if x is 6, as the input states here, that would actually also fit in the first piece because that's less than or equal to 6. So we're still going to use x plus 2, or I'll rewrite it as blank plus 2, and we put the input value of 6 in the blank. 6 plus 2 is 8, which must be our output for that given input. Thirdly, we want to find f of 8. Well, this time with 8 as an input, it fits into the second piece, which states when x is greater than 6. And so for that piece, we look at that function definition piece, which is where f of x equals 5. Notice when f of x equals 5, there is no x involved in that definition of the piece, which means there's no blank to write and nowhere to plug in the input of 8, which means f of 8 is 5. That output just stays as 5 in that piece regardless of what x is.